In this tip, we want to explain how is it that you find the angle theta if you know at what x and y coordinates the angle intersects a particular circle. First thing we need to know is how these coordinates are related to this angle theta. And the simple answer that always works, no matter what the radius of the circle is this. The x-coordinate is r times the cosine of theta, and the y-coordinate is r times the sine of theta. That's always true, but of course it simplifies. If you have a unit circle, then r is just 1, so this becomes cosine of theta and sine of theta for the x and y coordinates respectively. So this is the x and this is the y. Now, why is that true? Well, regardless of what the acute angle is, if we draw the triangle like this, the side opposite the angle will have a length, that's the y-coordinate, and the side adjacent to the angle will have a length that is the x-coordinate. So the cosine of theta is the adjacent over the hypotenuse, and we just fill this in now. In general, this has radius r, this opposite side, that length is the height, and this adjacent side, that length is the x-coordinate. So the adjacent is x over r. That's the cosine of theta. We multiply through by the r times the cosine of theta is equal to x. And likewise, sine of theta is the opposite, well, that's the y-coordinate, over the radius, that's r, multiply through by the r times the sine of theta is equal to y. So, and I don't like my times mark there, it's so messy, let's use a dot. So, r cosine theta is the x, r sine theta is the y. In the case of a unit circle, then those go away because they're just equal to 1. All right, so let's use those formulas to figure out the angle here. Well, we actually have two formulas that come out of this. We have x, that's 13 over 85, and let's just label that. X is equal to the radius times the r times the cosine of theta. Now, we could compute the radius here, but I'll just tell you ahead of time it's 1. So I'll justify that in just a moment. So we have x, 13 over 85 is equal to the cosine of theta. So cosine theta equals 13 over 85, and therefore theta is the inverse cosine of 13 over 85. And that's something we can estimate with our calculator. That is an exact answer right now, our inverse cosine of 13 over 85. So let's turn on our calculator. You want to make sure you're in degree mode here probably, if you want the answer in degrees anyway. I want the inverse cosine of 13 divided by 85. And I get theta is equal to about 81.2026 degrees. Now, if I did it for the sine, it should work the same, right? So if y is on the unit circle is 84 over 85, then the inverse sine of 84 divided by 85 should give me the same answer, and it does. You can see those two right next to each other. They are exactly the same. So this angle is a little better than 81 degrees. Now, it could very well be that you come across a problem that will just simply tell you, as I did here, that you're working with a unit circle, the radius is 1. If it didn't, how could you find out if it's a unit circle? And if it's not, how could you find out what the radius is? Well, it's this thing again. It's the hypotenuse, that's the radius, has length, the square of x, the square root of the square of x plus the square of y. So r squared is x squared plus y squared. That's the Pythagorean theorem. you take the square root of both sides in order to find out what r is. And in this case, it's 13 over 85 squared plus 84 over 85. And then you just can check this with your calculator. So I want the square root of the sum, 13 divided by 85 squared plus 84 divided by 85 squared. And in this case, we came up with 1. So sure enough, this is in fact a unit circle. Now, they're not always unit circles, though. So let's take this one, for instance, where I've tried to draw this pretty much to scale here and say that the point of intersection is at the point 1, 4. So what is this angle theta here? Well, in this case, I am going to have to compute the radius. R squared is x squared plus y squared. So you take the square root of both sides. One squared is 1. 4 squared is 16. So r is the square root of 17. Now that's an exact answer, and it's a good one. If you wanted to have a decimal approximation, of course, the calculator would work very well for that. But we're going to leave it right just as that is right for now, because I would like to compute this angle theta. Well, you could sketch in the right triangle if you wanted, right? And you'd say that the sine of theta, let's say, last time we used cosine, so I'll use sine this time. Sine of theta is the y-coordinate, this side, divide by the hypotenuse. It's opposite over hypotenuse. And we just computed the hypotenuse. That's root 17. So theta is the inverse sine of 4 over root 17. And we get about 75.9638. So here's an exact form for the answer. Here is a decimal approximation. Okay, we want to do 2 more of these now. Only these examples will go outside of the first quadrant. By staying in the first quadrant, what we did is guaranteed that our angle was positive and that it was an acute angle, less than or equal to 90 degrees. So what happens if that isn't true? Well, let's take this one, for instance, and now I'm not going to try to draw these to scale at all. I'll just try to sort of rough them in. If we say that that point of intersection is at -2, -2, that means we're to the left and down from the origin. And the x and y coordinates are the same, so we would be down around in here. And our point of intersection is -2, -2. So we'll be doing things pretty much the same as we did before. We're going to find our radius, and then we will try to compute the angle. Now, the thing is, though, that we're going to start working with reference angles. So this is the triangle that we're going to work with. And this will get us this side and this side. But then we have to figure out what this total angle is around here, because our trig function is just going to give us the reference angle. So zooming in a little bit, we're after this angle right here. And what we know is that the coordinates of this point are -2, -2, so that side is 2, that side is 2. Of course, negative simply means that it's left and down, rather than, say, right and up. Therefore, we can compute the radius. The radius is the square root of x squared plus y squared. It always is that. X squared is 2 squared, 4. The negatives are lost when you square, right? Minus 2 squared, again, is 4. So that's the square root of 8. And if you want it in a nice reduced form, it's 2 root 2. It's 2 square root of 2 squared times the square root of 2, right? You could take these apart this way. 2 times 2 is 4 times 2 is 8, and the square root of 2 squared is 2. So 2 root 2 is the radius. And now we would like to know this angle here. Well, as you can see, it's not going to matter whether we take the sine or the cosine. We're going to get the same answer. Let's take the sine in this case. So opposite over hypotenuse is 2 over 2 root 2. So that's 1 over root 2, or some people prefer to write that as root 2 over 2. It doesn't matter. Both are correct. And now we want to know what theta is. Theta equals the inverse sine of 1 over root 2. I'll take it in that form. That's convenient for the calculator. All right, now we can do this on our calculator. And if we do, we'll come up with 45 degrees. But actually, we don't have to, because we should recognize this as one of our special angles. A 45-degree angle is certainly the case if you go the same distance in both the x and the y directions. Your reference angle will always be 45 degrees. Or you could say this way, we memorize this triangle right here. A 45, 45, 90 triangle has hypotenuse 1 and legs of length 1 over root 2. So if you got this memorized, then you just recognize that and you're done. If you don't, then your calculator can do it for you, but it's an extra step. Also, calculators don't catch it when you push a wrong key, right? However, your memory, so 45 degrees is what this is, but that is the reference angle. So back to our original diagram here, we know that this angle in here, we know that this angle in here is 45 degrees, but this angle here is 180, so we have altogether theta must be equal to 180 plus 45, and that is 225 degrees. So that's the angle theta in this case, from here all the way around to here. 225 degrees would get you to a point minus 2 on the circle that has radius 2 root 2. So that's the answer to number 2. Okay, for the last one, we want to know what is the angle if our central angle intercepts a circle at point 2 minus 7. Well, 2 is positive, minus 7 is negative, so it's right and down. This one is quite a bit more in size than that one, so that must be we're down in this location somewhere, so you have more length in the y direction than you do in the x. And we have a picture something like that. So our coordinates go in here, 2 minus 7. We're going to need to know the radius, and then we want to know the reference angle, and then the angle all the way around. Remember, the reference angle is always the angle that's formed with the x-axis, not with the y. So there's our right angle, and our trig functions will give us this angle in here. Okay, first of all, let's find the radius. The radius is equal to the square root of x squared plus y squared, 2 squared, plus minus 7 squared. And that's the square root of 4 plus 49, that's 53. So root 53 is our radius, and we can compute either the cosine or the sine Let's take, say, the cosine this time. Cosine theta is the x-coordinate over the length of the hypotenuse. Now, when I'm doing it by this method, by the way, if I had picked the y-coordinate instead, I would still be calculating this way. The sine of theta is 7 over root 53. I'm not including that negative right now because if I included the negative, it would in this case it would just indicate that I'd rotated the angle down rather than up. But that doesn't matter to me right now. What I want to know is this acute angle inside of this particular triangle. So on this method, I really don't put the plus or minus on the x or y at this stage because it really just is not that helpful to me. Later on, we'll talk a little bit more about how to make use of those inverse functions when you do have the negative in there. But right now, it's easy to avoid. So the inverse cosine of 2 divided by root 53. We come up with approximately 74.0546. Or had we done it the other way around, would have said that it's the arc sine, the inverse sine of 7 over root 53. And in either case, you get 74.0546. So those are the same. That's, of course, in degrees. Now, that does not answer the question, though. The question is, we want to know what the angle is. What we have computed is the reference angle. So the reference angle is 74.0546. And from the geometry, looking at the picture, we know that if you come all the way around, you'd have 360 degrees, and then we've got to back up by this amount of the reference angle. So the theta that we're looking for is 360 minus this reference angle, 74.0546. And our calculator can do that for us. We have 360 minus, well, I've got it stored in memory, so let's just pop it in there. 285 .9454. And that's degrees. Alternate way of doing that is we could have said, well, we know across here is 90 degrees. We've used up 74 and some change in here, so this angle could also be computed. 90 minus the 74.0546 gets us to about 15.9454 in here. And then we could say, well, 90, 180, 270 degrees to get around to the fourth quadrant. And then we have to add this little bit, which is this angle that I just computed, 15.9454. That gets us to 285.9454, which is the same answer as we got before anyway. So there's multiple ways of getting at that. But what I want to emphasize right now is when we're doing the geometry, you generally will find it easier to work the problem if you go after this reference angle, then sketch your picture. It doesn't have to be very accurate at all, and figure out the total angle once you have the reference angle done.